so thanks for having me. Today I'm going to talk about joint work with Mirek Mirek, who's at Rutgers, and Terry Tao, who's at UCLA. So I learned about ergodic theory in grad school, and I used Ben Green's notes. And so I wanted to start with how he introduced ergodic theory. So sort of informally, suppose X is a set and T is a map from X to itself. If you take a point in X, the basic question that ergodic theory seeks to study is how the orbit of X under the iterates of T, quote unquote, equidistribute. So I haven't really told you what equidistribute means yet. I'm gonna impose enough structure for this question to be meaningfully posed, but I think I'm gonna just illustrate this phenomenon with some examples. So example one is familiar to maybe people in discrepancy theory or analytic number theory. So in our first example, our space is going to be the torus, which we identify with the unit interval. And our set map is going to be the point transformation that sends X to X minus alpha mod 1. So we know that when alpha is irrational, you can integrate continuous functions by approximating the integral by the Cesaro sum. So in particular, for any point X, if you look at f of x minus alpha, f of x minus 2 alpha, all the way up to f of x minus n alpha, you divide by 1 over n plus 1. This is going to uniformly approximate your integral. Okay. Second example. Again on 0, 1, this time we're going to let T be the so-called doubling map. So what it does is it takes a point, it doubles it, and reduces mod 1. So for instance, an eighth goes to a quarter, goes to a half, goes to 0. And the statement is that for almost every X, these Cesaro averages converge to a half as n goes to infinity. So the conclusion of, if you parse this, this turns into sort of a strong law of large numbers phenomenon for almost every X. So for instance, if you were to represent X in its binary expansion, so you choose epsilon 1 of X, epsilon 2 of X, and so forth, so that you can represent X as the sum. Then the statement is that for almost every X, if you count up the number of terms j less than n, so that epsilon j is 1, you average, and you count up the same number of terms j less than n, so that epsilon j is 0, both of these numbers tend to a half. And in this case, we say that X is normal. So to make our discussion of equidistribution rigorous, we impose measure theoretic structure on our spaces and transformations. So for the rest of this talk, X mu T will be a measure preserving system, by which I mean X mu is a probability space and T is an invertible measure preserving transformations. For functions on our space, we define Tn f of X by f of Tn of X. Okay, so our previous two examples fit into this framework. So broadly speaking, ergodic theory is the study of the dynamics of functions defined on X under the action of these measure-preserving transformations. And the classical objects of study are these Cesaro averages, as we've seen. And the main question is to what extent, if any, these Cesaro averages converge. So in our first example, we saw uniform convergence. In the second example, we saw almost everywhere convergence. And for the bulk of this talk, I'm just going to restrict to the Hilbert space setting. So unless I say otherwise, every function that I reference from this point on is going to be square integrable. Okay, with this in mind, there are two types of convergence that we consider. First, norm convergence. In this case, we view these Cesaro averages as a sequence of vectors, and we ask whether there's some vector in L2 to which these Cesaro averages converge in norm. And the second regime, which is what I'll focus on more, is pointwise convergence, in which case one actually seeks to evaluate the limit in a pointwise manner. So the two classical ergodic theorems, which were proven around the same time in the early 1930s, due to von Neumann and Birkhoff, dictate that these Cesaro averages converge both in norm and pointwise. So again, I'm mostly going to focus on the pointwise regime, but I'm briefly going to discuss the norm regime, which is better understood. So for instance, classical Hilbert space technique, namely the spectral theorem, for instance, can be used to address the norm convergence of the Cesaro averages, or even Cesaro averages along polynomial orbits. So we understand these averages when applied to a single function really quite well. On the other hand, once you start considering averages of more than one functions, the complexity really increases rapidly. So the departure point for the modern theory of multiple ergodic averages is Furstenberg's ergodic theoretic proof of Szemerédi's theorem. So let me start by recalling what Szemerédi's theorem says. Suppose that you start with a subset of the integers of positive upper density. So by this I mean a fairly large set. In particular, this is a set so that I can find an increasing sequence of intervals inside of which the relative density of my set stays bounded away from 0. And the conclusion of Szemerédi's theorem is that for any k greater than or equal to 2, there exist infinitely many progressions, x minus n, x minus 2n, all the way up to x minus kn that live inside your set. And it's important for this talk that the k equals 2 case, which concerns 3-term arithmetic progressions, was first established by Roth. So the reason why this is connected to ergodic theory is by the work of Furstenberg, who invented this correspondence principle that allowed one to deduce this sort of Euclidean Ramsey, or this discrete Ramsey theoretic statement from an ergodic theoretic one. So I'm going to present a result of Hoskrah and Liebman that's a bit stronger than what Szemerédi proved, but sort of captures the same idea. So here's the theorem. Suppose I take a bounded function and I consider these multilinear ergodic averages. So I multiply TNF, T2NF, T3NF, all the way up to TKNF, and I average an n. Now each one of these averages is bounded. So in particular, it's in L2. And if I study all of these vectors, there's some L2 vector to which these vectors converge in norm. So almost 20 years after Furstenberg's proof, Furstenberg and Weiss established the following norm convergence result for nonlinear ergodic averages. So in this case, it's a bilinear theorem, and it says, suppose I take two bounded functions, and instead of considering TNF, T2NG, I consider TNF, Tn squared G, and then I average an n. Again, these are bounded functions, so the average is bounded. In particular, it's in L2. And the result is that these averages converge in L2 norm. And by applying sort of this Furstenberg correspondence principle, we arrive at the sort of non-linear Roth type corollary, which says that suppose you start with a subset of the integers that's large, as positive upper density, that there exist infinitely many progressions, x minus n, x minus n squared. So Roth's theorem concerned 3 APs, x minus n, x minus 2n. This concerns nonlinear arithmetic progressions, x minus n squared. So this result of Furstenberg and Weiss extends all the way up to, in some sense, Miguel Walsh's norm convergence result, which is very, very general. It concerns multiple ergodic averages really of any degree of multilinearity and any combination of transformations, provided that they slightly commute and that they generate a no-potent group of transformations. So this is very, very general. But the pointwise situation is far less understood. So for instance, we know how to prove norm convergence for Cesaro averages along polynomial orbits. We've known how to do that for a very long time. But it wasn't until Bourgain's work in the late 80s and early 90s that we understood how to prove pointwise convergence for ergodic averages along polynomial orbits. As far as the bilinear theory is concerned, basically the strongest thing we knew was due to Bourgain in the early 90s. And here's the statement. Suppose that k is an integer and f and g are bounded functions. And the conclusion is that the bilinear ergodic averages, TNF, TK, and G, average and n, converge almost everywhere. And this was strengthened quantitatively by Michael Lacey to cover sort of a wider range of integrability. But qualitatively, this is as good as we get. So roughly speaking, the program behind pointwise convergence is to establish Walsh's theorem in the case of a single transformation, at least. So the goal is this: prove that for every collection of m polynomials and any m bounded functions, the multilinear ergodic averages converge pointwise almost everywhere. So here's what we can say so far, and this concerns the bilinear setting. So suppose that P is a polynomial of degree at least 2, that F is in LP, G is in LQ, P and Q are not 1, and 1 over P plus 1 over Q is not much bigger than 1. So you can think about P and Q as both being a little bit less than L2. The conclusion is that these bilinear ergodic averages converge pointwise almost everywhere. So basically you're saying, suppose that F and G, neither of them are too spiky, and that when you multiply them together, they don't get too spiky either. And then the conclusion is that when you form these bilinear ergodic averages, you converge pointwise almost everywhere. And even though I didn't state this, this result holds not just on a probability space, but also on a sigma finite measure space as well. But in what follows, I'm gonna just restrict to the case where F and G are square integrable and where a polynomial is just n squared. So this is just what Furstenberg and Weiss considered. And this already sort of encodes a lot of the difficulty that we encountered. Before I want to talk about the proof, I want to give sort of a combinatorial consequence of our result that sort of contrasts it to the Furstenberg-Weiss theorem. So here's how it goes. Suppose that I take a random subset of the first n integers with density delta. Then from any vantage point x in our set, we would sort of expect E to behave randomly with respect to sampling along the parabola, in the sense that the probability that x minus n and x minus n squared is in E sort of factors is the product of the two probabilities, which is equal to delta squared. So with this in mind, we might expect that if you look at the first n different numbers less than p, the percentage of those n, so that x minus n and x minus n squared is in E, simultaneously would be about delta squared. In other words, you'd expect that from any vantage point x in E, E would behave sort of randomly with respect to sampling along this parabola. Okay, so there's an obvious arithmetic obstruction. There's no reason for general set of density to be random. You could just take a coset, for instance. But it turns out that this is really the only obstruction to this sort of randomness, this random sampling phenomenon. So here's the nonlinear Roth type corollary, which I think of as sort of a condensation of singularities type phenomenon. It says that there exists a single sort of physical location that accounts for many different nonlinear arithmetic progressions. So more precisely, suppose I take a subset of positive upper density, and I let epsilon be any tiny error parameter. The conclusion is that once you pass to an arithmetic progression, for all large times, there exists a single vantage point, xr, so that the percentage of my arithmetic progression, of the first n terms of my arithmetic progression, so that xr minus pn and xr minus pn squared both live in my set, is greater than delta squared minus epsilon. So this says that if you take your arithmetic, there's some arithmetic progression, so that if I look at the first n elements, the first n plus 1 elements, the first n plus 2 elements, all the way up to the first r elements, and I count how many terms xr minus pn, xr minus pn squared both live in my set E, I get the random score, delta squared, up to the small epsilon of error. So the way I think about this is there's some vantage point, xr, in my set, so that my set E behaves randomly when I sample along this parabola. We have this arithmetic obstruction. We have to be sensitive to this sort of coset phenomenon. But once you take this into account, E does behave randomly somewhere when you sample along the parabola. Okay, so on to the theorem. So before we talk about the bilinear formulation, it's helpful to just understand the two special cases where first G is constant, in which case our bilinear averages just reduce to the Cesaro averages. And second of all, when F is constant, in which case our averages reduce to Bourgain's averages along the squares. So the Cesaro averages I'll continue to refer to using Cn, and I'm just going to call the averages along the squares Dn. So again, the Cn were studied by Birkhoff, and the Dn were the subject of Bourgain's work in the late 80s and early 90s. So here's what we know. For any measure-preserving system and any square integrable function, the Cn converge almost everywhere. In roughly 60 years, Bourgain proved that the Dn converge almost everywhere as well. So I want to talk a little bit about pointwise convergence. So we think about pointwise convergence as being very qualitative. In particular, a sequence converges if for every altitude t, there are finitely many balls of radius t, so that I can cover my sequence an using this finite collection of t balls. So I can trap my sequence an inside finitely many balls of radius t. And I'm going to use the notation script nt to denote the smallest number of balls that covers my set. So with this in mind, we can recast the statement that a sequence of functions converge almost everywhere if the map that sends x to the covering number at altitude t of the sequence of functions fn of x is finite for each t. So what this says is that for almost every x, there exist only finitely many balls of radius t that cover the collection fn of x. So the sequence fn of x is trapped in a finite union of balls of radius t. So to exhibit the convergence of these covering numbers, what we're going to do is we're going to try to prove a norm estimate that sends f to covering number of Cesaro average at each point, or similarly, that sends f to covering number of the averages along the squares. So again, we're looking at the image of these Cesaro averages at each point. And what we're trying to do is we're trying to say that at almost every one of these points, we can cover the image of these averages by finitely many balls of radius t. So this technique comes from martingale theory. And the estimate that we're going to try to prove is the following. For some r less than infinity, and in practice, you need to take r greater than or equal to 2, you want to show that in an L2 average sense, the number of balls of radius t that it costs to cover the Cesaro averages is like t to the negative r. And that's just what this estimate implies. So you take an L2 function of norm 1, you look at the orbit of all the Cesaro averages, and at a generic point, it's going to cost t to the negative r many balls of radius t to cover this collection, this image. And that's what we're trying to show. So this is just this seems like we're giving up a lot. We're trying to prove a quantitative estimate that measures sort of a rate of convergence rather than just deducing that the covering number is finite. But there's a huge technical advantage to quantifying. So the first instance of this type of phenomenon was due to Bourgain, who proved that for any r greater than 2, it costs essentially t to the negative r many balls of radius t to cover the orbit of the Cesaro averages in an L2 average sense. And in 2014, I proved the same result for the sequence of squares. And And in what follows, all of the estimates involving these covering numbers are going to be uniform in my altitude. So no matter what t you pick, no matter how thin, how skinny you look at your balls, it still costs t to the negative r many balls on average to cover the orbit of your Chisaro means. Okay, so we want to prove this estimate for our measure preserving system, but we have no sort of geometric information or metric information about our space. This seems like a very challenging problem. But there's this lovely principle of Calderon, which says that it's sort of the acting group that tells us where we should study our problem. Basically says that we're dealing with a z orbit, a z action, so we should study this problem on the integers. In particular, if we sort of consider maps that send n to tn f of x for each x, we can reduce matters to proving the following sequence space estimate. So if you pretend these sort of forward averaging operators are just Chisaro averaging operators where your measure preserving system is the set of integers with a shift. So just to recap, we started with a problem in about pointwise convergence, and we've reduced it to a problem proving an estimate really in discrete harmonic analysis. So we've taken a problem that's in ergodic theory and we've turned it into proving an estimate for sequence valued functions. So here's how we did it. We started by trying to prove a convergence statement in the dynamical system setting. We recast convergence and we reduced it to proving that the covering numbers of these orbits converge almost everywhere for each altitude t. We decided to prove this convergence by proving that these covering numbers satisfy a norm estimate. And then we transferred this norm estimate to the sequence-based setting. Now, this transference argument does not work if we just try to prove finiteness. You actually need something quantitative to transfer. And this is sort of the reason why we try to estimate these covering numbers more directly. So let's start with the linear averages. So it turns out that we can almost completely borrow the Euclidean theory. So if you look at these linear averages, you can just sort of use probability theory and a little bit of elementary Fourier analysis to prove the covering numbers satisfy the estimate you want. So the discrete theory and the Euclidean theory are very, very similar. And this analogy relies on the fact that if you look at the set of integers and you form the Minkowski sum of each integer with the unit interval, you get the whole real line. So as far as the squares are concerned, we want to prove a similar estimate, but we have this geometric issue. In particular, if we let O denote the orbit of the squares, so 1, 4, 9, 16, etc., the intersection of O with any interval is bounded by the length of the interval to the 1/2 power for every interval inside the integers. Or in the Euclidean setting, if we take the set of squares, we form the Minkowski sum with the unit interval, and we intersect it with any real interval of length at least 1. This is similarly bounded by the length of the interval to the 1/2 power. So from the perspective of dimensionality, the squares sort of act like a lower dimensional set. Right? So in the Euclidean situation, if we consider the trace t squared, as t increases, we get the whole half real line. Whereas if we consider the trace or the orbit of the squares, some set with a unit interval, we get a much smaller set. So the analogy between the squares in the discrete setting and the squares in the Euclidean setting completely breaks. Now, just as a non-example, if we're trying to prove the same jump counting estimate for the squares, we could just sort of change variables and reduce back to the linear setting using convexity. And again, this argument totally fails because there's no infinitesimal changing of variables in the integers because of the presence of a smallest scale, right? The integers are discrete. We can't infinitesimally reprice the real line. So this argument totally fails. So we have to try something different. And we try to use Fourier analysis. This is an L2 problem involving convolution operators. It makes sense for us to try to use the Fourier transform. So recall that the Fourier transform of a sequence space function, an L2 function, is given by summing your function against a character. And if we use this, we can express our averaging along the squares as a convolution with our kernel Kn, which is just a function that's 1 over n on 1, 4, 9, 16, all the way up to n squared and 0 otherwise. And if we use inversion, we can write this as our Fourier transform multiplied by the Fourier transform of our averaging operator inverted. So the thinking is if we somehow really understand the Fourier transform of our averaging operator, maybe we can make sense of what's going on, even though the geometry of the situation doesn't really help us. So Kn hat is an example of an exponential sum. And notice that the phase is quadratic. So this is a somewhat subtle object. So I want to contrast this to the linear case, where the pertaining exponential sums have a linear power of n. And in this case, we can completely understand what's going on by summing a geometric series, or just by sort of Taylor expanding beta around the origin. In particular, everything we need to know about these multipliers in the linear setting is determined by the distance from beta to the 0 frequency. There's no oscillation really going on. You just look at how close, how big, you look at the magnitude of beta, and this tells us everything you need to know. On the other hand, our multipliers are Gauss sums, and to analyze them properly, you need the circle method from analytic number theory, which was a technique developed by Hardy and Littlewood in their study of Waring's problem. So I think about the circle method sort of probabilistically. In particular, this exponential sum is really just an average of n mean zero pairwise independent random variables. And for probability theory, you might expect to have some small power savings. But there's sort of an arithmetic obstruction to this type of reasoning, which comes from potential correlation of the phases. Beta maps to beta n squared. So the best example of this is just seen by evaluating Kn hat at the point 1 over 3. So if we do this, when n equals 1, we get e to the 2 pi I 1 squared over 3, which is e to the negative 2 pi I over 3. When n equals 2, we get e to the negative 2 pi I 4 over 3, which is the same as e to the negative 2 pi I over 3. When n equals 3, we get e to the 2 pi I 9 over 3, which is 1. And then the cycle just repeats itself. So in particular, even though formally speaking, we're averaging n independent random variables, because of this arithmetic correlation, we're really actually only averaging 3 of them. There's this periodicity that comes into play. So in particular, this multiplier does not decay. It's O of 1. So if you kind of continue this reasoning, you end up with the following distinction. So our exponential sum is large and interesting whenever beta is n close to a rational number with an n small denominator, in which case we say that beta lives in an n major arc. And you can make this quantitative very easily. And in the other situation, our multiplier is negligible because the probabilistic intuition kicks in. So back in physical space, what this tells us is that what we really need to do is figure out what these convolution operators do to functions like chi-q, which are sort of an indicator function of q to the 100, L1 normalized, but multiplied by this oscillatory prefactor, which is formed just by summing the unit group mod q. So you sum up over all the characters whose frequencies are co-prime to q. And the relevant scaling here is q is less than n to the 0.01, or a little bit less. So n is very large compared to q. And what you're trying to understand is what these convolution operators do, not to these L1 normalized bump functions, but to these L1 normalized bump functions weighted by these oscillatory factors. So what this meant for Bourgain was the sort of problem in multi-frequency harmonic analysis. What he did was, more precisely, if you take these sort of oscillatory L1 normalized functions and you convolve your initial data with one of them as follows, we'll call this FQI. What Bourgain was interested in doing was understanding destructive interference between superpositions of these convolved functions as QI varies. So what he did is he said, okay, let's take some threshold Q, let's add up a bunch of these convolved functions where QI, all the QIs are different but approximately Q. Let's convolve these with our kernels, and let's count the covering number of the resulting operator. So if there's no covering operator involved, and you're just simply looking for the behavior of your kernel applied to superposition of these convolved functions, it's very easy to estimate. And you get a strong savings of something like q to the negative a half due to some orthogonality in Fourier space. But Bourgain was interested in understanding how quickly these averages converged, how many balls of radius t it costs to cover them all at once. So again, with fq given by this convolution, so I'm averaging over the first q to the 100 integers weighted by this exponential sum. The following estimate holds. So for each r greater than 2, whenever you have about q squared of these functions, where each qi is pigeonholed to be about q, you lose log squared q in your estimate. So if there were only one kn and you weren't worried about jumps, you'd get a bound of q to the negative a half. What Bourgain did is he said, even if you take a look at this covering number and you measure oscillation in this fashion, you only lose by a log squared in q. So in other words, there's a huge degree of destructive interference. These FQIs barely interact. So just to summarize, when we wanted to prove pointwise convergence of the linear averages, we transferred the problem to a quantitative estimate involving convolution operators on the integers. We used the Fourier transform to figure out what we should be looking at, and then we estimated the jump functions. And this estimate that Bourgain proved was sort of the hard analytic core of his work on pointwise convergence. It's very, very subtle and used Banach space geometry and sort of martingale theory, not just harmonic analysis. And I should say that this scheme is pretty straightforward on L2 because Poincarel's theorem allows us to quantify every quotation heuristic very easily. Okay, so what this means for us is that we have a similar approach. We consider the bilinear averages in the measure preserving setting. We pass to the sequence-based setting, and we try to prove an L2 cross L2 to L1 estimate on the covering numbers of these averages. So in Bourgain, we put BNF here, and we had an L2 to L2 bound. Here we have a bilinear average, and we have an L2 cross L2 to L1 bound. But the scheme is the same. But there's a big problem, which is that we don't have Pointcarel anymore. So we can't just use the Fourier transform to tell us what to do. So what we did instead was we used some quantitative work of Sarah Palouse and Sean Prendeville concerning non-linear Roth phenomena. So our key inverse theorem, which kind of kickstarted our whole argument, was the following. Suppose I take two functions that are bounded in magnitude by the indicator function of some interval where this interval is size about n squared. And let's say that the L1 norm of bilinear average is almost as large as it could be. So it's not n squared, but it's n squared up to logarithms. So it barely fails to be of maximal size. And the conclusion is we can find some arithmetic progression of nearly maximal length and a very small gap size so that our first function concentrates its L1 norm on this arithmetic progression. So more precisely, we can find some q of size log n to some power so that when we convolve f along the arithmetic progression qn, not quite n times, but almost n times, the resulting L1 norm is nearly maximal. So everything's off by a logarithm. But it's very, very mild. So what we did is we started with this inverse theorem, and we came up with this additive combinatorial sort of Fourier analytic argument that allowed us to turn this inverse theorem into an approximation argument that told us how to chop up our multipliers. So we used three different techniques. We used a tool from Discrete Harmonic Analysis, which is sort of a discrete Littlewood-Paley theory, which relies on some superorthogonality properties of certain collections of rational frequencies. We used the Hahn-Banach separation theorem to guide sort of an inverse theory. And we used the Vinogradov mean value theorem to prove some quantitative estimates. But the upshot of this is we found ourselves in a situation that was very similar to what Bourgain did. So in particular, we needed to study these bilinear averages applied to pairs of convolved functions with this oscillatory term, where the least common multiple of Q1 and Q2 is of an appropriate size. So in Bourgain's situation, we are looking at superpositions of these convolved functions where we applied Kn to these superpositions. Here we're looking at the bilinear setting, but we're still interested in sort of understanding interference between sums of these averages. So again, our challenge was to efficiently estimate the jump counting number of these types of superpositions. So this is a little bit difficult to parse. But what it says is that if we assume that the least common multiple of these QIs is Q, and we only restrict ourselves to scales that are very large, then we get a small amount of savings over the trivial L2 cross L2 to L1 estimate. So what this says is that if you take two L1 normalized functions, f and g, and you form these convolutions, then it's going to cost t to the negative r times q to the negative c naught many balls of radius t on average to cover the set of the orbit of these functions. So one more time, I look at this superposition of averages, and I ask how many balls of radius t it costs to cover the superpositions as our scale increases. And what this estimate says is that we can do a little bit better than t to the negative r. As our modulus increases, we gain a small amount. Not a full half power, but some positive amount. The key to proving this estimate, which was the second main ingredient that we used to prove our theorem behind the work of Sean and Sarah, is sort of this non-linear Roth theorem in a cyclic subgroup setting. So here's the statement. Suppose delta is bigger than 0 but very small, and P is a prime that's polynomially large in delta inverse. Then for any Q that's a power of P, if you take a subset of Z mod QZ that has relative density delta, then the conclusion is that this set contains a nonlinear arithmetic progression, x minus n, and x minus n squared. And when Q is just a prime itself, this theorem is known, at least in the finite field setting, due to initially Bourgain and Chang. I think Sarah might even have a stronger quantitative estimate. But this is the key additive combinatorial result we needed to prove this previous theorem. Other ideas that we needed were sort of martingale methods. We used symbolic space geometry. And finally, we used some oscillatory integral techniques over the p-adics. And our argument, I mean, Bourgain's argument required sort of a synthesis of Banach space geometry ideas, harmonic analysis, and number theory. And we actually needed more physical space ideas as well. We really did need the sort of additive combinatorial arguments and these sort of non-concentration estimates for polynomials over the p-adics. So moving forwards, there's sort of a more refined inverse theorem of Sarah that concerns the multilinear setting. And using this, Mariusz and I expect to prove the following result. Suppose I take m polynomials of distinct degrees, and I take m bounded functions, and I form the multilinear ergodic averages. Then the conclusion is that you should have pointwise convergence almost everywhere. And this should hold whenever the product of your functions maps into a space that's a little bit bigger than L1. A similar quantitative phenomenon holds. As far as polynomials of the same degree are concerned, the model problem concerns two quadratic polynomials. So what we really would like to see is whether or not, if you consider the bilinear orbit P1NF, F1, P2N, F2, where P1 and P2 are quadratic, we'd like to see whether or not these guys converge almost everywhere. So again, Bourgain did linear. We could do linear quadratic, but we'd like to do quadratic. Another question concerns the genericity of our results, just in terms of density. So in particular, suppose that AN is a sequence that grew like n to the c, where c is non-integer. Can you prove that these guys converge almost surely? You know, or for instance, you might suppose that AN is randomly generated, a sequence of hitting times. Can you almost surely prove that these guys converge? That's it.